Hey gang, welcome back. Lecture 55, Chemistry Part 13, lucky 13, okay? We're going to talk about the pH scale, dealing with acids and bases. Remember, acids are things that donate H plus ions or protons. Notice an acid, if it donates an H plus, a proton is not happy with a charge, right? If you look around nature, look around the world, look around everything that you touch is neutral. There's no electric charge. So obviously the lowest energy state for any system is to not have a charge, either plus or minus, to be neutral. So when you have acids that want to give up protons, these protons aren't happy. They don't want to be by themselves. They want electrons. So the acids put out these protons and they're looking for electrons. Where do you get electrons? Well, one good place is a metal. Remember, metals, electrons are very free to move, and so an acid would rip out those electrons from a metal. And so acids, this is the reason acids are very corrosive. You don't see, in a laboratory, you don't see acids in a metal container. They're always in glass. Why aren't they in metals? Because metals like to give up electrons, and these protons, these hydrogen ions running around, love electrons, and they want to rip them off and cause things to corrode, okay? And again, bases are proton acceptors in the Lowry description. All right, so at room temperature in Kelvin, 20-something degrees Celsius, room temperature Kelvin, about 300, it's okay. Water, just a glass of water, cup of water, bottle of water, naturally dissociates to a very small degree. Okay, very few molecules actually dissociate. So the water molecule breaks up into a hydrogen, a proton, plus an OH minus, hydroxide ion. Okay, the H plus then floats around, but it hooks up with a water molecule to form hydronium ions. Okay, so there's going to be some concentration of hydronium ions and some concentration of hydroxide ions. Okay, now I said not many of these molecules at room temperature dissociate. Obviously, at a higher temperature, if you heat up water, more molecules will dissociate, break apart. Why? Because as you add heat, you're adding kinetic energy. You're adding energy and the system can break up. But at room temperature, when I say not many H2O molecules dissociate, in fact, I want you to see these arrows means it goes both ways. So Saturday night, it's very popular. So this hydrogen, this water molecule breaks up and goes back and forth. Okay, it doesn't stay as a hydronium. Okay, now only 1 in 10 million molecules actually dissociate on average at room temperature. 10 million is 10 to the 7th. So one water molecule at a 10 to the 7th is a concentration of 10 to the minus 7. So we have water, again, the arrow going both ways, forming, I skipped the step for the H plus ion, hydronium plus hydroxide. Now let's look, this is balanced, this equation. H2O goes to H3O plus OH. So if I had 5 water molecules, you'd make 5 hydronium ions and 5 hydroxide ions. If the concentration of water molecules dissociating is 10 to the minus 7, then the same concentration of hydronium ions are being produced, 10 to the minus 7. And again, same coefficient, so the same concentration of hydroxide ions are produced, 10 to the minus 7. Now if we look at this, okay, now when I write a square bracket, square brackets, put X in there, it doesn't matter, denotes the concentration of X. So if I do this, square bracket Na plus 1, this symbol with the square bracket Na plus 1 would represent the concentration of sodium ions. So square bracket implies concentration. Okay, so let's look. We have 10 to the minus 7, 10 to the minus 7. So we have the concentration of hydronium ions times the concentration of hydroxide ions is 10 to the minus 7. 10 to the minus 7 is 10 to the minus 14. Add the exponents. Remember, add the exponents. So the concentration of hydronium ions multiplied by the concentration of hydronium ions, oops, I said it backwards, right? Hydroxide ions is 10 to the minus 14. So let's talk about logarithms, all right? Here's where you say, no, not logarithms, please, I can't do math as it is. I can't add fractions. What are you doing to me? Why? I don't want to know logarithms. Look, for what we need logarithms for, piece of cake. So just watch what we're doing, all right? Simple. Even you can do it. Even you, okay? Don't give up yet. All right, so logarithms, not so bad. Look, the log of 10 to the second power, is 2. Log of 10 to the third is 3. Log of 10 to the ninth is 9. The log of 10 to the minus 18 is minus 18. The log of 10 to the 44 is 44. Minus the log of 10 to the minus 8 is plus 8. Right? Because the log of 10 to the minus 8 is minus 8. When you take a minus of that, you get plus 8. Minus the log of 10 to the minus 11 is plus 11. Minus the log of 10 to the minus 4 is plus 4. Okay? That's what we need to know about logarithms. That's it. Piece of cake. End of discussion. Okay? So now, we want to define pH, percentage of hydrogen. Okay? It's the hydrogen ions. So pH, let's see. Here's what we define pH to be. Okay? It's minus the log of the hydronium concentration. Hydronium concentration. So just watch. So let's see. If the hydronium concentration is 10 to the minus 8, what is the pH? Well, the pH is minus the log of 10 to the minus 8. So it's plus 8. That's pH. If a solution has a hydronium concentration of 10 to the minus 2, the pH of that solution is minus the log of 10 to the minus 2 is plus 2. Man, isn't this hard? Wow, I don't know. All right, if the hydronium concentration is 10 to the minus 13, then the pH of this solution is minus the log of 10 to the minus 13 is plus 13. If you get this wrong, I'm gonna get you. All right, now remember, here's our rule. The concentration of hydronium times the concentration of hydroxide ions must be 10 to the minus 14. So pay attention. This is a little tricky for some of you. If the concentration of hydroxide ions is 10 to the minus 6, what is the pH? Now, I'm not telling you directly the concentration of hydronium ions, but I am telling you the concentration of hydroxide ions. Okay? Well, if the hydroxide concentration is 10 to the minus 6, and the hydronium times the hydroxide concentrations must be 10 to the minus 14, if this is minus 6, 10 to the minus 6, this must be, the hydronium concentration must be 10 to the minus 8. It has to add up to negative 14. So the pH of this solution is minus the log of 10 to the minus 8 is plus 8. So if the hydroxide concentration is minus 6, the pH is plus 8. What if the hydroxide concentration is 10 to the minus 10? Well, the pH is 4. Why? Because the hydronium concentration must be 10 to the minus 4, minus the log of 10 to the minus 4 is plus 4. If the OH concentration is 10 to the minus 1, then the hydronium concentration must be 10 to the minus 13, and then when you take minus the log of 10 to the minus 13, you get plus 13. And finally, if the OH concentration is 10 to the minus 9, the hydronium concentration must be 10 to the minus 5, so the pH is plus 5. Wow, isn't that hard? Oh, gosh. So now you're an expert on pH and concentration. Okay, one final thing I want to talk about, and that is basic neutralization reaction. Neutralization reactions. Okay. Here's what we have. We have an acid. When you add an acid plus a base, you always get water plus whatever is left over is a salt. Okay? That's what we define to be a salt. You know the joke? Two peanuts were walking down the street. One was assaulted. Different kind of salt. Okay, so let's see. I have some practice problems. Okay, so let's look. HCl. What is HCl? Hydrogen chloride, remember it's a gas. Aqueous, AQ, plus KOH, aqueous. What is KOH? Potassium hydroxide. Well, we get water out, plus, can you see what comes out? KCl, right? Okay, and this should be, I think, aqueous, and this is a liquid. There's my water, so potassium chloride is my salt. Okay? Let's look at this. 2HCl aqueous plus, let's see, I think we'll mix some magnesium hydroxide. MgOH2. Remember, magnesium is group 2, so it has a charge of +2. I'll write the oxidation numbers to review. And this has an oxidation number to hydroxide of -1, so this is magnesium hydroxide. Okay? What do we get out? We get 2 waters, liquid, plus, looks like MgCl2. MgCl2. Okay, I think that's still aqueous. Okay, I'll put AQ. Okay, so this is my salt. The potassium chloride is a salt. Acid plus base, water plus salt. Acid plus base, water plus salt. Right? We'll do another example. Okey-doke. Let's see, we have, nitric acid. Aqueous. HNO3, right? And we're going to add that to barium hydroxide. Barium is group 2, hydroxide is -1, so we need 2 of these. Okay, we're going to get out water. That's a liquid. Plus, can you see what we get? Barium nitrate, right? BaNO3, 2. Okay. Good. So, water, and this would be the salt. All right, one more. Let's see. Let's do phosphoric acid. So, remember phosphoric acid was triprotic, H3PO4, and again that's aqueous. PO4 ion, remember, was -3, and protons neutralize that, so that's sulfuric acid. That's phosphoric acid, and we'll add some calcium hydroxide. Okay, calcium is +2. This was -1, so that's calcium hydroxide. What do we get out? Well, again, we know we get water out. Okay. Look, we have 2 times 3 is 6 hydrogens. 3 times 2 is 6 hydrogens. So we're going to need water. We need 12 hydrogens, so it's going to be 6H2O. That's liquid. Plus, can you see what we're going to have? Calcium phosphate. Is that right? Calcium. Ca, remember that's a +2, phosphate, PO4, calcium's +2, phosphate is -3. So remember how to add these? We have to make 3 calciums with 2 phosphorus, and I believe that this is a solid. So this is a solid. I'm going to put an S. Okay, so there's my water, and there's my salt. All right, so acid plus base, water plus salt. Acid plus base, water plus salt. Okay, so you see salt is not just NaCl, right? Table salt. Okay. There are many types of salts. There's thousands of salts. Okay, but in neutralization, you take an acid, you take a base, and they neutralize it with no pH, and then you get water plus a salt. So in your stomach, right, you're neutralizing. If you take a Tums or some other antacid, what it's doing is it's adding a base, probably something like calcium carbonate, and you're adding it to the HCl, aqueous, okay, and then you'll end up with water plus whatever salt. What would be the salt with calcium carbonate, right? You figure it out, okay? So calcium chloride, CaCl2 would be the salt. All right, that's it. Enjoy yourself, be safe, and see you next time. Peace out.